Okay, so good afternoon to everybody. Today we have the pleasure to have a speech from Dr. Mohammad Reza Pendar. He is researcher fellow and instructor in the Department of Mechanical Engineering at the University of Victoria. He's specialized in fluid mechanics through a combination of experimental, computational, and theoretical approach. His research is focused on developing cutting-edge CFD tools to design quieter and more energy-efficient marine vessels by predicting and mitigating cavitation-induced underwater noise. And today he is going to present his work entitled CFD Tools for Predicting Cavitation-Induced Underwater Radiated Noise. Please, Dr. Pendar, you may start your presentation and sharing your screen.
Hello, everyone. Good afternoon. I really appreciate and thank you for participating in this presentation. I'm Reza Pendar, postdoctoral fellow and researcher and instructor at University of Victoria in Canada. Today, I want to present for you our work entitled Development of CFD Tools for Prediction of Cavitation-Induced Underwater Radiated Noise. In these days, radiated noise, especially from marine vessels, it's very important. The negative effects of anthropogenic noise, specifically produced and generated by marine vessels, a kind of masking signals, especially marine mammals using for communication and echolocations. Marine mammals, acoustic for them is very important, and they used the acoustic for navigating, reproduction, foraging, communication, and other normal activities. And the underwater radiated noise is nowadays is global issues, and for deeply analyzing the signature of radiated noise, we generate a comprehensive novel platform to deeply modeling hydroacoustic and hydrodynamic features of propulsion system of marine vessels. And here you can see the progressive steps we did. First, we generate a 3D CAD models. For example, after generating design or optimization design of the available vessels, we run the case in different operational conditions. In this case, advanced ratio and non-dimensional numbers like advanced ratio cavitation number and also the Reynolds number, it's very important, and the rotational speed of propeller of vessels and also the free stream velocity is very important. In our CFD models, we use the SOAR in combination with very strong LES, large eddy simulation models, and also using volume of fluid for track the liquid and vapor interface. For noise analysis, we used different models. Fox-Williams-Hawkins acoustic model is very strong and very useful model, which can be used for prediction of noise in far-field areas. And also we employ the continuous wavelet transform methods and fast Fourier methods. After modeling the case, and also recording the data by some we call microphone. This microphone located over different regions of the computational domain. For example, over the surface of blade, over the surface of rudder, and in far field area by recording the data, specifically the pressure and velocity, we could a kind of predict the noise level. After analyzing the noise, we also using the machine learning for two goals. First, for prediction of flow features, and second, by using the machine learning methods, decrease and also a kind of diminish the interaction between the marine mammals, acoustic and noise generated by the marine vessel to have the minimum interaction between them. We have broad range of marine vessels. You can see here. You can see a broad range of marine vessels here. We, in our case, to show a kind of the versatility of our modeling, we consider two types of vessels: large size of vessels, BC freeze, which operate between mostly this free, Quinnipiac Bay free, operate between the Victoria and also the Vancouver. This very large size vessel, the diameter of this vessel is 4 meters, which is very large. And also we considered a small size rudder and propeller with size of around 30 centimeters for considering the small size vessels. Computational domain, it's very important to at first prevent the blockage ratio, and then the size must a kind of satisfy the to capture the wake structure generated by the propeller, and also the and also the boundary condition you can see here we consider for our modeling. Another parameters in numerical modeling is mesh. For a kind of independent analysis of our mesh, we consider two parameters of thrust and torque. And in our modeling for large size vessel, after analysis, we obtain that a mesh with 14.2, and for a small size 15.2 million cell is very important. The size of mesh must be fine because LES modeling, large eddy simulation turbulence model, is very sensitive to mesh, and also we specifically by purpose consider this area very small size of mesh to capture the wake structure generated by the propeller. Here you can see for the mesh for a small size vessel. Validation in numerical modeling, it's very important. For validation purpose, we consider three different methods. First, for quantitative and qualitative analysis of our case, we consider the wake features, and this is our numerical result, which compared with experimental result, we it shows the strength of our modeling because we could successfully capture the tip vortex, hop vortex, their instability, and other flow features like mutual inductance, first and second grouping of the hop pattern, and other features. And also for global performance parameters like thrust and torque, with accuracy of less than 1%, our model could capture the flow and could predict the thrust and torque coefficient. And also you can see here the cavitation over the surface of blade. It's very close to what we obtained in our experimental setup. Nowadays, CFD, accurate modeling of CFD is very important, but visualization, also another parameters, you a kind of by details show what you obtain with your CFD modeling. For example, here you can see 5 different useful methods we employed for visualization for a kind of demonstrating our result. We used the 3D isosurface Q criterion, which is very important parameter in showing the wake pattern and vertical structure behind the propeller. Is a surface of vapor volume fraction, a kind of we call cavity cloud. You can see the blue zone here over the surface of blade, and 2D visualization by, for example, coloring by the vorticity, velocity, and other parameters. We could by details analyze what we obtain, and also is a surface of is a surface of extreme wise velocity, and we located microphone over different location. In experimental work, for example, locating a microphone over the surface of blade and rotation of that blade, it's very difficult or impossible. But in numerical modeling, it make analyzing of the flow, it make it very easy. We located, for example, microphone here, microphone over the surface of blade in different region, and also over all over the computational domain. By recording all parameters of flow, analyze the noise generated by propulsion system. Here, I would explain for you the vertical structure. We considered 3 different patterns of rudder with different wavy pattern. This tubercle rudder diminish the noise level, and by manipulating the wake structure behind the surface of a rudder, specifically in higher rotational speed, for example, in higher a kind of deflection angle of the rudder in maneuvering condition, it manipulate the wake structure and also diminish by 10 dB, 10 decibel, the noise level generated by propeller and rudder. The 3 different important region: a stable, transition, and unstable region behind the propeller. Analyzing of them, it's very important, and considering the tip vortex, trailing edge vortex, root vortex, hop vortex in different region I mentioned, it's very important and very useful analyzing of them to using this data for a kind of new design of propeller. Here we deeply analyze in different views the wake generated by the propeller over the surface of rudder, colored by vorticity magnitude, pressure coefficient, and also the velocity magnitudes. Tubercled, a kind of rudder or baby rudders by counter-rotating vortex pair and low pressure. Here you can see low pressure zone, and also by changing the wake pattern can be used for new design of radars, new generation of radar. In modeling of propeller, marine vessel propeller, rotational speed is very, you can see, compared to previous slide, by intensifying the swirling flow, you can see the very rapid reorganization and recirculation pattern and a kind of small size vague structures. These small size structures directly affect on the radiated noise level. As I mentioned, 2D visualization, it's very important. For example, you can see in different deflection angle of radar. For example, here is 20. And in different rotational speed, the wake pattern behind the propeller significantly changed. For example, here by increasing the rotational speed from 300 to 600, twice of the rotational speed, you can see the tip vortex pattern completely changed, and the flow and also the hub vortex and the flow became completely fully turbulent condition, and directly we have the higher noise level. Here you can see, for example, propeller with the deflection angle with 20 degrees of the deflection angle, the flow pattern behind the rudder completely changed. Another parameters which cause higher noise level over the surface of propeller, and it's very important to minimize the level of that, is cavity over the surface of propeller. The cavity specifically generated in higher rotational speed, affecting the multiple frequency range. And here you can see, for example, in higher rotational speed, here we have much more higher sheet cavitation, hub cavitation, and also tip cavitation. And using the tubercle rudders, leading edge rudders, diminish the cavity over the surface of rudder, as you can see here, and it can be useful in decreasing the cavitation, generated cavity over the surface of rudder also. In our modeling, after deep analysis of wake structure, and also the fast Fourier transform analysis of noise recorded by the microphone, we could kind of organize the frequency levels. For example, the blade frequency, we reported that mostly related to the tip vortices and blade trailing edge vortices. Hub blade frequency related to tip vortex pairing, paired helix, and also mutual inductance. And narrowband peaks in medium to high frequency, mostly related to cavitation structure, and also lower or equal than shaft frequency related to the a kind of far field area of the wake, and related to wake progressive weakening and a slight mindering and a kind of cavitation collapse and shedding. Here you can see for example, considering two cases, with and without considering the cavitation, you can see around 12 decibel we have lower a kind of cavitation, increase the noise level around overall sound pressure level around 12 decibel. Why, considering that noise level, it's very important. Why these frequencies for us is very important? Because by analyzing this frequency generated by propulsion system of marine vessels, we could compare with the noise level uh, marine mammals using in their activities. For example, here you can see, for example, the dolphins. This is the frequency range dolphins used in their activities, and for example, the humpback whales here in this region, the Vancouver Island. We have a lot of humpback whales. They use the lower frequency range. By comparing these two acoustic levels, we could kind of uh, redesign our vessels to diminish the interaction between these two noise sources. Another parameters is overall sound pressure level in different operational condition. We could obtain that, and these parameters is very important to a kind of showing the noise level of the marine vessels. And here you can see be compared in different operational condition. By increasing the rotational speed, we have much more overall sound pressure level, and also going far field from the propellers as a source to far field area, also the noise level decrease. One priority and importance of numerical modeling of marine vessel, we can kind of by using the data of that microphone, the sound pressure level over the surface of propeller during the rotation and also the rudder, we can capture that, we can compare of that. And here, for example, in this slide, we showed that tubercle leading edge rudder improving the acoustic under higher maneuvering condition. For example, here the 20 degrees of deflection angle. Our goal is decreasing the noise level generated by vessel, but we must find the sweet points between the noise level and also the operational and also the operational efficiency of vessels. It's very important because by optimizing the configuration of propeller and optimizing the wake we analyzed in previous slides, and also decreasing the cavitation level, and find the sweet point between these parameters and also minimum level of noise, we can produce a new design. What we did after deep analysis of marine vessels, we suggested to add some parameters over the propeller, both large and a small size of propeller. We added some propeller boost cap fin, you can see here. We analyzed and we considered different patterns. Normally, in very a small size of industries, they use just a simple rectangular fin pattern. What we did, we analyzed different fin. These patterns of fin, these 9 patterns of fin, which we consider, they have the maximum lift to drag ratio, and by considering of them over the cap fin of propeller, we found out that the NACA 4412 and E63, these two patterns can obtain the maximum thrust and also minimize the hub vortex, and also the manufacturability of this pattern is it's not that much difficult, it's easy. and also they are cost effective. Another pattern we used another component we added to propeller to increase the thrust and also at the same time decrease the noise level. We use the duct over the surface of propeller and also using the modified cap pattern, a kind of we call diverge cap pattern instead of converge. We use diverge cap pattern to here you can see it's very important to a kind of decreasing the Hop vortex as one of the main noise source. We use this for showing the flexibility of this component. We also use over the propeller of BC Freeze, Quinnipiac Bay BC Freeze, and the vortex generator component. We use them to a kind of deflect the flow pattern for increasing the thrust. We use the, as I mentioned in previous slide, the modified cap, a kind of divergence cap fit pattern for reduce the hop vortex generated and also related noise. And the fin installed over the boost cap fin here with these two patterns, they are useful as a vertical structure diminisher. As a concluding remark, I can mention, in our work, in first step, we deeply analyzed the dominant wake morphologies and cavitation features. For example, the wake structures like tip, root, hop, and other structures, and cavitation like sheet cavitation, hop, and for example, tip cavitation. Analyzing clear interactions between these features and noise generated by these features, the mechanism of that, and in-depth analysis of some important noise parameter like overall sound pressure level, acoustic spectrum level, and also the frequency range of different parameters. And by, for example, using different methods, we suggest new design, new generation of marine propeller with components of divergence boost cap fin, with fins, and also with vortex generator and duct. From our work, we published recently 2 papers in physics of fluid in 2024 and 2025. For more information, you can check them. And thank you so much for your attention.
Okay, thank you so much, Dr. Reza Pendar, for your presentation. It was very informative.